The average human circulatory system is made of approximately 60,000 miles of veins, arteries, and capillaries. The heart often gets the credit as the workhorse of this system, but how does blood actually make its way from your feet back to your chest to be pumped around for another cycle? In a healthy person, the calf muscle acts as a second heart, squeezing the vein and pushing the blood forward. To keep that blood from falling back down, your veins use one-way valves. These act as check valves, ensuring the blood takes a one-way trip back to the heart. But when these valves fail, gravity wins. This is chronic venous insufficiency, or CVI. When valves don't close, blood begins to pool, increasing the pressure until the vein walls start to leak, leading to varicose veins, painful swelling in the surrounding tissue, skin changes, and in severe cases, the formation of blood clots. It is estimated that 10% or 25 million adults in the United States have some form of CVI, with about 6 million experiencing more severe symptoms of the disease. Popular treatments like compression sock therapy only manage symptoms by squeezing from outside the leg, but they don't fix the broken pump or faulty valves. Our sponsor, Becton Dickinson, challenged us to change that. They asked, can we design an implantable system to assist in return blood flow, mechanically bypassing the broken check valves without requiring a physical connection to outside the body?
To return function of collapsed valves, we need to provide a pressure gradient powerful enough to encourage forward flow and push blood up to the next working valve. The mechanism at first seems simple. However, designing a device in this size and in a biological environment leads to many complications. We dove into research immediately, trying to identify and solve every problem at once. How big is the vein? What flow rate and pressure do we need to create? Do we use a rotary pump or a squeezing sleeve design? Should we power it with ultrasonic energy, electromagnetic fields, or something else entirely? How can we mathematically model our system? How do we find a way to integrate it into a stent? How could the device cause clotting? How do we seal the motor? How do we ensure the device is hemocompatible, biocompatible? It adheres to EMF limits and ISO standards. How do we squeezing sleeve design? By our preliminary design review, it was clear that our focus was spread too thin. Medical devices take an average of 3 to 7 years to bring to market, and we had a project timeline of 8 months. So we took a step back and narrowed our scope to focus on creating a scalable proof of concept that answered the two most important questions. Number one, can we wirelessly power a device this small? And number two, can that device generate a pressure head needed to move blood? These two questions became our critical design elements and paved a pathway forward.
Our finalized design consists of 3 major parts: the impeller, electric motor, and wireless power transfer system. Looking first at the impeller design, our goal was to optimize geometry to move fluid as efficiently as possible while minimizing the power input and rotational speed needed to reach our target pressure. We started prototyping with a standard FDM 3D printer, but after the first few iterations, we realized we needed a method with higher resolution to better understand the relationship between impeller geometry and pressure. We pivoted to stereolithography or resin 3D printing to achieve higher resolution and improved manufacturability. For rapid testing, we used a simple small brushed motor directly wired to our power supply and held in place with a custom 3D printed motor holder or makeshift stent. While half the team worked to test and optimize the impeller design,
the rest of us focused our attention on figuring out how to power the system. Not penetrating the vein wall was one of our biggest requirements for our device, so we've started by evaluating possible wireless power solutions. We researched inductive and magnetic resonant coupling, as well as ultrasonic power solutions, but chose to investigate the 2 magnetic power transfer methods because of their ability to transfer higher levels of power. The operating principle of our power transmission system is electromagnetic induction. By passing an AC signal through a sender coil, we can then generate a magnetic field with alternating flux direction. This magnetic field can induce an AC signal in a separate receiver coil, which we can then rectify into a DC signal to be used by the electronics implanted in the vein. We hit 2 major roadblocks during the design process. First, the function generator couldn't provide the current necessary to create a magnetic field strong enough to power anything, let alone a motor. Second, in our initial design, we proposed that the sender coil be placed outside of the body, while the receiver would be implanted inside the vein. In practice, this distance resulted in losses too great to power the pump. We solved these problems by sourcing high output transmission coils and by changing the design to feature concentric power transfer with the sender coil placed just outside the vein wall rather than outside the leg. Moving forward with this design, we hand wound receiver coils to fit within the diameter of the vein wall. After attaching these coils, our pump still fell short of our pressure head requirement. To overcome this efficiency gap, we sourced new receiver coils that provided improved performance while still meeting our vein size constraint.
To accurately compare results between designs and replicates, we created a custom testing apparatus to emulate the Venous system. We used an acrylic tube with the same diameter as a portion of the common femoral vein and filled the apparatus with a 50-50 mixture of water and glycerin to closely mimic the viscosity of human blood. The testing apparatus has two modes, one to test static pressure head using a ruler to measure the change in height of the fluid column, and a second to measure flow rate by allowing fluid to fill a graduated cylinder over a set amount of time. This setup allowed us to iterate on our impeller design in real time, measuring exactly how much pressure head and flow rate each variation could produce. To verify our impeller design, we removed the wireless power transfer variable and used a wired motor prototype to isolate the performance of the impeller. Using a high-efficiency Maxon motor, we were able to exceed our pressure head requirement of 6.59 millimeters of mercury, while the motor consumed 120 milliamps of current. We next worked to verify the wireless power element of the system. Using our off-the-shelf coils, we were able to generate and even exceed the required pressure head. However, these coils are 4 times larger than the vane geometry, so they would not work for our final design. From there, we tested a set of 10mm off-the-shelf wireless power receiver coils that would fit within the vane. These coils are able to transfer 150 milliamps of current. While this full setup, including the motor and motor driver, cannot be powered by these coils due to a higher voltage requirement, this wireless system can theoretically supply enough power to drive the motor alone.
We started this project with an ambitious goal, solving CVI by implanting a pump into the femoral vein. We have proven that a miniature impeller can generate the necessary pressure to push venous blood to the next valve, and that electromagnetic power transfer can wirelessly power the pump. As with any breakthrough, our project represents the first step in moving this idea from concept to clinical reality, and several engineering hurdles remain. Future work should focus on making the device biocompatible, integrating the motor circuitry to the implant housing, creating a catheter-based delivery system, and shrinking the wireless power transfer system. Our design is a research-oriented proof of concept and is not a patient-ready product. Nevertheless, we believe this work carries genuine significance by pursuing a solution that targets the underlying dysfunction rather than merely managing its symptoms. Our project takes a meaningful step towards truly resolving chronic venous insufficiency.